Okay, the recording started. The name of the course Theory of Structures, and then the course code is 2 CENG 255. Um, with this course, I think almost everyone should be enrolled on the V campus. Um, I would entreat all of you to just cross-check, just go to V campus, make sure that you have um, your name added to the class group in case I might have missed somebody. All right. Um, so the mode of teaching again with this course primarily would be the online on Fridays from 10 to 1 p.m. on a weekly basis. Um, and so we plan on starting tutorial sessions. So with this tutorial sessions, what's going to happen is that you have the TAs come around and then take you guys through some questions, some examples, maybe so that it can expand your knowledge base and also your understanding on these on the various topics that we'll be covering throughout the semester. So just like the class, I mean, my lectures are compulsory, right? You get marks for attendance, and for that same reason, I also want to make the tutorial sessions compulsory. Okay. Over the years, I've made it voluntary, but then sometimes students just do not show up. Okay. And then these tend to go against them, especially when there's time for exams, quizzes, and also, I mean, both the midterm exams and then the final exams. Okay. I'll discuss with the TAs going forward. I mean, with the class rep, Kelly, and then we can discuss what time will be favorable or convenient for all of us so that we can attend the tutorial sessions. The plan is that so the TAs will come. So you meet in the classroom. So the TAs will come. They'll put a question on the board, or maybe hand over maybe notes or papers with the questions on it. Then you, the students, will first attempt the questions. All right. So the TAs are there more as a guide than anything else. They're not there to teach you per se, but they are there as guides. So what will happen is that they will come to the classroom, put the questions on the board. All of you will attempt it, and then where there are challenges, then they will try to resolve some of these challenges for you guys. So um, that is the plan for the tutorial sessions. I think if you go on the, let's try to get the file. If you go on V Campus, you'd hopefully for those of us who have been to V Campus this past week, you'll see that I've posted a copy of the course outline on the V Campus for us to have access to them and then plan the semester accordingly. Okay. So I'll just upload that on the screen that we can also have a look at it. So let me find out where it is. Then quickly upload that we can discuss from there. Just a second. Okay, so I have here the course outline. So I can move it up a little. Great. So hopefully there are no mistakes in the course outline. Everything here should be self-explanatory. So it's a 3 credit hours, which means that we should be teaching every 3 hours. I mean, 3 hours every week. Yeah. So the excuse me, we would be looking at a so the office consultation hours, or maybe the time where you guys can meet me if you have any concerns whatsoever. I think again I'll discuss that with the class rep, and then I'll let you guys know what time would work for all of us. All right. Again, this will also be online for now. So the same with the tutorial sessions, we have to come up with a time. I'm looking at 1.5 hours for the tutorial sessions, or should I say anytime between 1 hour and then 1 hour 30 minutes. I think this should suffice for tutorial sessions. If there's a need to go beyond the 1 hour, the 1 hour 30 minutes, the maximum we can never do will be 2 hours. Okay. And then that's again would have to be discussed and agreed on by the your class rep and then the TEs. Okay. So why theory of structures? Why do we need to study theory of structures? Theory of structures as a course is part of a broader structural analysis component. Okay. I think I can write, do I? Okay. I think I can write on the side. Hopefully, yeah. So you guys have done you've done basic structures, right? So that's your CENG one, I think 5.5, if I'm correct. And then so that is like the first component of the structural analysis topics. And with basic structures, typically your focus would be on the fundamental structural analysis, right? So you get to understand what the force mechanism is, understand what's the name, moments, go through how to resolve forces in the respective Cartesian directions. And then you also focus on the um, support conditions, basic support conditions, understand what loads are. We'll try and go through some of them. So understand what loads are, understand what what's the name, internal behavior in terms of internal forces, and then be able to pretty much analyze statically determinate structures. All right. So the goal is that we do external analysis and then internal analysis of statically determinate structures, which is mostly forces and loads. Okay. So that's the basic structures components. Okay. Then what's happening? Okay. So then we also have this topic or this course, which is theory of structures. And I think second semester, you do structural analysis as a course. I mean, it's a funny name to have because everything we are doing is structural analysis, right? So to have only one particular course being called structural analysis is a bit interesting, but I mean, they all fall under structural analysis. Okay. And I think in a final year, if I remember, something is messing up my pen. I don't know what it is. You should do I think there's dynamics. I think there's dynamics, yeah. Structural dynamics, and so there's structural dynamics. This should not mess up today, please. structural dynamics. Okay, so that's again structural analysis, but this is more like an advanced version where you are focusing more on earthquake, seismic behavior, and all of that. And I think there should be structural engineering. Yeah, structural engineering. The course I think is divided into certain components. There's an analysis, and then the design component. The analysis is something very small, and I think normally it's on composite analysis of structures, and uh, and then we do the design, right? But normally these courses, by the time you're done with your 4 years over here, these should be uh, enough. I mean, to give you some comprehensive understanding of the topics that of structural analysis. These two in final year are what we call elective courses, right? Optional. So you get to choose between structural analysis, structural engineering, or dynamics, and I think transportation also one of these other courses. So in final year, you get a chance to do the core, where everyone will do those courses. Then there are a few courses that you are given the options of choosing the one you want to go with. Okay, so that is in your final year. Okay. So why do we have to study um, structural analysis, or for that matter, theory of structures? Okay, and the reason has to, for all 5 cases, the reason has to do with the fact that we need to understand the structures. So the structures is in quotes that we interact with. Structures can be buildings, they can be bridges, there could be dams, there could be, maybe with bridges, we can even have different types of bridges and all of that. There could be retaining wall, water tanks, both one in ground, one above ground. And when these things are around us, we need to understand how, one, they interact with us, two, also how they interact with other materials, right? Or how they behave when other materials, or in this case, other loads are placed on them. All right. Um, because if you don't know how they interact, you would, for example, if we are looking at water tank, so let's say one very big water tank. If we don't know what how much water should, sorry, usually it's supposed to be at the top. Okay. How much water should be in the tank? We just put in the quantity of water. What you see happen is that with time, these, the behavior on the water on the tank can cause the tank to collapse. All right. And then that will lead to failure. Okay. Recently, there's been some with the Akosobo Dam spillage, uh, which has caused a lot of flooding across the southern uh, part of the Volta region, and I think some part of the eastern region. And the reason behind, so the engineering reason behind the spillage is that a dam is just like a water tank in a way. So just to explain an idea, usually this is the basic design of a cross-sectional wise, the design of of a dam. That's typically how the Akosombo Dam is designed. So you have water behind it. Okay. So this dam is designed to carry a certain height of water. Okay. So this is your height of water. Let me just exaggerate the height of the dam a little bit upwards. Yeah. So the dam is designed to carry a certain height of water. Um, okay. So which means that there was a professional who understood how much load water can apply, or how much pressure water can apply to a surface area, and they use that information to calculate the total load coming from the water. And then they came up with certain parameters that, okay, if we get a water of this height, let's say 250 millimeters, 250 meters height of water, we can design a structure that can hold the water up to this height, which means that once the water exceeds that height, the that structure will not be able to hold that water or retain or support that water, right? Or let's say the force of the water will exceed the strength of the structure, in this case, the dam, and then that can cause the dam to collapse. Okay. So what happened was that once it's been raining a lot this year, um, towards August, September, there's been a lot of rains in Ghana. So which means that uh, there was a possibility that the water impounded behind the dam was going to exceed its height, its should I say control height or limit. So they had to open the sluice gates so that they can let go some of the water, because once the water exceeds the design height, it's going to topple the dam. All right, and then that could cause a more catastrophic disaster. All right. Um, I'm not going to talk about the handling process of the whole spillage, how the maybe there wasn't enough awareness and all of that. I mean, that's the social component of it. Anyways, engineering is a bit of also has a social component to it, yes, but I'll not go into that. Okay. But as engineers, this is what we do. Okay. So before you could do any of this, you need to understand the behavior of certain parameters, right? Understand loads, understand materials, be able to know how you can transfer the loads from one point to the other, okay? So that you can end up putting up safe and reliable structures, which can be used for the benefit of occupants or anybody that it's meant to be used for. All right. So that is basically the rationale behind engineering. I mean, so, structural engineering. Okay. Um, there are different methods or different approaches that are used to analyze structures. Okay. So many of them. We'll try and look at the different approaches, right? Some are suitable for certain scenarios, whilst others are not, depending on what the loading conditions and also what the structure behavior would be. Okay. So at the end of this course, I mean, by I think January or February, um, the goal is that everyone in this class should have had some understanding of how to analyze structures using some of the methods that we have studied. I mean, that we would end up studying the course. Okay. So yeah, attendance is 5%. I think assignments will be 10%. I might vary them a little bit going forward. Then the mid-semester exams, I think I should make the mid-semester exams rather 20. I'll figure some out. I'll figure that one out. So let me just put here, this is subject to change. So that you don't hold my neck when I change it later on, right? So this is subject to change, but for now, attendance is 5%. Assignment is 10%. Mid-semester exams is 15%. Quizzes will be 10%. And then the end of semester exams will be 60%. So I think when you sum everything up, that is 100%. Okay. Since this is a mostly a structural analysis course, questions, examples, um, tutorial questions, they would most likely be heavily um, calculation based, right? It doesn't mean that all questions will be calculations based, but about 90 or so percent of the um, material that would work with are typically calculation based materials. Okay. So for the books that we'll be using for this particular course, I think I have about how many? Four of them. There are so many out there. So these are just the ones that usually I go through. The most common, do I have it here? Yeah. So the most common is the Hibla structural analysis, where I think this should be the most recommended text. So the most recommended texts, and then you can also look at the Casimali structural analysis textbook. It tends to complement the Hibla. If you go to the library, I think you find this other textbook, this Indian origin textbook. Let me if I can remember the name. I think there are different volumes. So there's a structural analysis, and this is by SS Bavikati. I think that's the name. Let me get the spelling correct. Bavikati. So there are three volumes. All right. So there's the volume 1, volume 2, volume 3. I don't know which of them, which is which though, but you can always, I mean, when you go to the library, you can just look at the content, the table of content, and then you can tell which ones you are looking at now. I think the volume 3 is mostly for next semester. So I think the volume 2 should be for this semester. Yeah. It's a fairly useful book to have around. So for those of us who like to visit the library a lot, you can find these textbooks over there. All right. Then there's the Williams, MS, and then Todd. It's also a good book. Just that the Todd book is not only on structural analysis, but it also delves into strength of materials, right? Looking at the internal behavior of the material component of the structures. All right. Okay. So I think we have 12 weeks of lectures. Our 8th week would be for mid-semester exams. Things might change a little bit, but we have minimum 12 weeks, or should I say maximum 12 weeks of lectures. And these are the breakdown of what we will be studying throughout the semester, right? So for today, we'll introduce ourselves to the course. We'll look at the objectives, which we are doing right now, and also do a review of our basic structures. Whatever we learned in first year, I'll do just a quick recap of it, summarize everything, just an hour and then half, and then so at least it becomes a refresher for us, and then we can build on that to study some other more I won't call them challenging, but more interesting topics going forward. Yeah. So these are the courses. We'll be focusing on, I think, three main areas, right? Three main areas. So we have three. Oops, this is quite. So three main areas. So we are looking at deflections. So that is area one. Deflections, yeah, I got it correct. We're looking at deflections, that is area one. Then we are looking at so let me say analysis. Why is one capital and one is so let me make it this way. Analysis of statically indeterminate structures. Okay. Indeterminate structures. Okay. So this analysis will basically be how to find reactions and how to find your shear force and how to find your bending moment and all of that. And you draw your diagrams with it. All right. So that's the statically indeterminate structures. Then we can look at the influence lines. Uh, for process. Okay. So these are the um, 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 three main topics that we will be looking at. But then there are a few subtopics below. All right. So if you look at the course content, you'll see that deflections, we have, so under deflections, let me do a bit of magic. Hopefully the magic works. Let me move you down. Great. Okay, so the magic works. Okay. So under deflections, we have a few of them. We have deflections. We'll look at deflections into detail, what deflections mean and all of that going forward. So for now, if you don't understand what deflections are, it's fine. We'll look at it later. So we have what we call so we use what we call the geometric methods to find deflections. And with the geometric methods, an example is the moment area. So we have the moment area method. Okay. Then we also have the conjugate beam method. Conjugate beam method. Then let me also put the double integration method underneath this one. It's slightly different, but that's fine. Double integration method. Okay. Then we have what we call what was the name? The energy method. Okay, so the energy method. Okay. So the energy method, we have what you call the unit load method, or the method of virtual work. And then we have others like the Castigliano's method. Okay. We will do the Castigliano next semester. All right. We'll do the Castigliano next semester, but then we'll deal with the unit load method in this particular course. Okay, so the unit load method. All right, so the geometric energy, so those are the deflections, how to calculate deflections. Then the statically indeterminate structural analysis. We have again a few. Let me put this one down a little bit. For this semester, we will be looking at just one, and then that's the three moments. What did I just do? Okay, so we'll look at the three moments equation method. Okay, there are quite a number of them. There's the slope deflection method. There's a moment distribution method. We have the force method, right? Some of them are called displacement methods, some are called force methods. We'll look at some of these things. I think second semester will focus heavily on some of these broader displacement and force methods, right? But for this semester, we are looking at the three moment equation method. Okay. Then we also have influence lines, right? We have influence lines for beams, which I'm sure you did that in your first year. And the beams are typically statically determinate beams. And this semester, we will be looking at influence lines for statically determinate trusses. Next semester, we'll focus on influence lines for statically indeterminate structures. Okay. Yep. So this should be um, a summary of the things which we will be looking at throughout the semester. Hopefully, we're able to cover everything, all right, so that we don't rush or we don't leave some out because they are all important to understanding the structural analysis behavior. So here's a breakdown. Everything, the three main divisions should fit into the 12 weeks, hopefully. Yeah. So let's look at the overview. Um, Overview of basic structures or structures as we learn them in or we learned in first year. Um, I think as part of your um course content, you define what a structure is, right? So a basic definition of a structure. And so in simple terms, a structure is defined as any object that can pretty much carry a set of loads or forces, sets of loads from one place to the other. Um, so, and it should be able to do that without um, collapsing. So once it collapses, then it's no longer a structure, right? So without collapsing or deforming excessively. Okay. So it means that there would be some deformation, right? But the deformation should not be excessive because once it's excessive or once the deformation is too much, there are a few things that come into play. We'll discuss some of them going forward. All right. But typically, when there's too much deformation, that can also lead to the collapse of the structure. So there are a few things to note over here. So it should be able to carry carry some set of load and also transfer the load. So carry and transfer. So from one place to the other. So that is a transferring component. And it should do all of these without collapsing or deforming excessively, right? And the highlighted green then becomes the characteristics of a structure. It becomes the characteristics of Mm. So the first thing is that what you should be able to carry loads. If it can carry loads, then it's not a structure. Okay. Then transfer these loads. Okay. So with the transfer of the loads, you should be able to transfer the loads to another structure or another structural component. Okay. Or to the ground. Okay. Then it should also, of course, it should not collapse, so must not collapse. So should not deform excessively. And also I think the final one is when it's carrying the loads, um, it should cause some forces to be generated within the structure, right? And that's where the load transfer system works. Okay. So the applied loads, I put it into writing. Applied loads should cause oops, spelling forces like that to be generated in the structure. Okay. And that's one of the reasons why we are able to find some of these internal behavior, like the axial forces, the shear, and the bending moment. Okay. So these are the characteristics of a structure. I believe we know what these things are already, just a recap of them. So what are loads? Okay. We have different types of loads. Any any weight on a structure pretty much act as a load, right? So we have different types of loads and we can categorize the loads based on their directions. So we can group the loads based on directions of the loads. Okay, so the direction in which the loads are applied. We can also categorize them based on how the loads are distributed. So based on distribution, then even also based on duration, how long the load stays on the structure. So some of them will definitely overlap others, but normally you find these subdivisions in terms of how loads are categorized. Okay. So in terms of direction, um, so in terms of direction, we have what you call gravity loads. Okay. And gravity loads are typically vertical loads. Okay. Normally vertical loads. Okay. And two of the most common types of um, gravity loads are what you call permanent, or some will say dead loads. Okay. And these are loads that, as the name implies, these are loads that stay with the structure throughout its or for a majority of the lifespan of the structure. Okay. One of the ways to like basically define a permanent load on a structure is I mean an example. Let's say if you have a table, all right, and you place some items on the table. If you turn the table on its side, right, and then you shake the table, materials or objects that do not fall off the table are deemed to be what? Permanent on the table, right? So then those would qualify as permanent loads. So simply put, any loads or any objects that stays with the material or stays with the structure pretty much throughout its lifespan, then will be qualified as what's the name? Having or being permanent. The other vertical load, which again is common, would be imposed. Okay, and we call these ones live loads. Okay. Let me just add this over here. Some examples of the permanent loads are the self-weight of the structure. Okay, so self-weight of structure. I'll just go through this quickly. I believe we already have that information. You also have finishes, right? Finishes, the ceilings, the tiles, the 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 light fixtures, cabling, all of these are finishes, right? And they tend to stay with the structure throughout the pipes that runs through or the conduits that runs through the entire building for the electrical wiring and all of that are part of the finishes. Then we have partitions, right? And with the partitions, let me put asterisks by it because sometimes we can have what we call permanent partitions, and other times so we can have partitions and then we can what's the name? We can also have partitions which are temporal, right? We can fix them the into the building and then remove them at certain times. And there are those that um excuse me, sorry. Okay. And then there are those that stay with the structure throughout, right? If you look at, I think, it's a block F, okay? The classrooms, I think on the ground floor, you would realize that, let's say F104A, F104B, there's some division, right? Some wood-like, plywood-like division between the two, right? Initially, it was just one long classroom, and then they put that wood wood-like material to divide the classroom into two. So that is a partition. Okay, so that becomes a permanent partition because this will stay with the building for a very long time. Okay, yeah. Now we have any permanent equipment. Permanent equipment, yeah. There are some buildings that when you go in there are certain equipment you find in those buildings, which were designed to be part of the buildings throughout its lifespan. An example would be an engineering laboratory. If you go to a well-resourced engineering laboratory, you'll find um, cranes, like overhead cranes, which are able to move things here and there. You can even find um, frame systems which are bolted or welded to the floor. A lot of things that, or a lot of equipment which pretty much are designed to be there with a structure throughout. So these are the permanent loads. Then we have, so with the imposed loads, they define occupancy. Too thick. They define the occupancy of the structure. All right. Or they define the use of the structure. So, for example, it's the same building that has been designed, but one could be used for a classroom, one could be used for a church, one could be used for an auditorium, maybe a theater, a museum, or even a stadium, right? So it could be the same concrete, it could be the same beams and all of that, but then the use of that structure would define pretty much even what name we give to the structure. Okay, so for example, in a classroom, students just come in, sit and go. Um, Most of the time, the tables and chairs they sit on are not movable. Yes, I know in Central, our chairs and things have been movable, but in other places, chairs and tables are where they are throughout, right? Now, if we should compare this to, let's say, a church, okay. So in Ghana, schools, students come and sit down, they are taught, they leave. Now in the church, things happen in the church. An example, like people come around, they jump, they shout, they dance, and you'll see that the behavior of the occupants in these two scenarios are different. Okay. And that would also define how to design the structures. So we can look at, so for example, if it's an office space, the load for an office space is normally about, I think, for office, it's about 2.4 kilonewtons per meter squared for an office. Then for residential, like say your house, it's about, I think, 1.9 kilonewtons per meter squared. For some auditoriums or theaters, like the National Theatre, for example, you could go all the way to about 4.8 kilonewtons per meter squared, right? So these are the different loads would apply to the structure based on the occupancy or the use of the structure. Then the other permanent load, gravity loads are what you call snow loads. In our part of the world, we don't have snow issues. So normally when we are designing structures, we don't include snow loads as part of our design process. But in other countries where there's snow, I think in the US, almost every state in the US, when designing, you have to include snow. I think apart from Florida, if I remember. Right. So the US, Canada, most European countries, Russia, all the way through to the UK, um, Australia, right? They also have snow. And even in South Africa, certain part of South Africa also has snow, right? So all of these have to be looked into depending on what loads you're likely to face. Okay. Then in terms of distribution, we have what we call concentrated loads. Okay. So we have concentrated loads. Or what we call point loads. Right. In reality, we do not have point loads. We don't have, we usually represent point loads by this arrow. It could be up or down, it could be left or right, it could be slanting, it could be in a direction, but usually is how we represent point loads. But in reality, we don't have point loads as a point, right? Hardly is there any load acting as a point. The reason why we call certain loads point loads is because when we compare the cross-sectional area, let's say the floor area, now we compare the position of the load. Okay. So even though this load has an area, a length and height, sorry, a length and width, the area of the load is very small compared to the floor area. right? So we can simplify that by saying that it is a point load, right? But then in reality, no loads are acting at a point. At least they act over a surface area, no matter how small that surface area would be. Then we have the distributed loads. And we have two of them. We have the uniformly distributed loads, which we normally call them UDLs. And then we have the varying distributed loads. So that's, some will call them VDLs, right? Their behavior is slightly different. In terms of the UDLs, they take, so as a structure, they usually take this shape. Right, so they act, okay. So they are a load distributed over an area, or in some cases over a length. Okay. They can, so usually they are drawn this way as a rectangular object, or in some cases, um, we just do this whole uh, a cloud-like whatever design just for that. We also have the, so for the VDLs, they are more or less, so the load will vary from one place to the other. So it could be trapezoidal in shape, or it could be triangular in shape. So triangular and trapezoidal depends. Okay, so these, it can be in any orientation, right? It can be, the loads could be vertical, the loads could be upwards, the loads could be applied towards the right, towards the left. It could be in different directions, but usually they have this, the two of them mostly follow the basic shapes. The UDL follows a rectangular shape, while the VDL, my U and V are about the same. So let me, okay. So the VDLs follow these triangular, trapezoidal, trapezium-like shape. Okay. So when analyzing them, you try to understand them as though they are shapes, and that makes the analysis fairly straightforward. Okay. So I think I missed something over. Let me just put over here. Let me. I don't know why. I think I forgot to. This is going to be a bit challenging. Does it work? Does it work? Okay. Why don't I bring you down a little? Okay. Let me just place something over here. I think I forgot. So we have the gravity loads. Then we also have the lateral loads. Okay. Loads that normally happen in the horizontal directions. I forgot to add that. Pardon me. I just state what the examples are, right? So we have the seismic loads, which we call the earthquake loads. Then there is the wind load. Normally, wind loads act as lateral loads. Okay. Normally, sometimes they can also act as vertical loads, but mostly they come as lateral loads. Then we have earth loads. Okay. So the loads of soils against the structure, right? I think most of you were on campus. I mean, the hostels you were living in were on campus. I think behind the girls' hostel also, if I remember, there is a basement, an uncompleted structure behind it. and pretty much the entire structure, it's in the ground. Okay. So the walls of that structure, let me just draw that, just draw something over here. So the walls of the structure looks like this. So this is the outside of the wall, and then the inside. Okay, so you have your inside like that. Okay. So this is where I think there are classrooms over there, if I remember. Yeah. So basement lecture theaters. So the inside it's in the ground. So the inside is hollow so that we can have our classrooms in there. But then the outside of the structure has soil, which pretty much is like the roof of the basement is almost at the same level as the ground. Okay. So we call this structure here, we call this one here a retaining wall. Okay, it has other names depending on what functions it's fulfilling, but it's mostly called a retaining wall or even a basement wall. And what is happening is that the soil outside, the soil here is pushing against this wall. All right, so it is a load on the wall, and engineers design against these loads. Okay, and usually when the load is pushing against the wall, we call it an active pressure or active earth loads. Okay. You do a lot of that in the, I think, soil related courses in, I think, second, third year maybe. So you do more into this active pressure and passive pressure as to explain the different loads mechanisms that the earth can have on a structure. Then we have the hydrostatic loads. I've mentioned something similar already, hydrostatic loads, which are the loads coming from impounding water behind the structure. So it could be a dam, it could be a water tank. It could even be a retaining wall. So even with with most retaining walls, because we have water in the ground, right? Groundwater. It means that when you are looking at the soil pressure acting on the structure, there's also water in there present. So you also have to look at the hydrostatic component of the loads. And all of these are, as engineers, we should be able to critically determine what the loads are. The hallmark of structural engineering is knowing what your loads are. Okay. What will separate a good engineer from an excellent engineer is first and foremost understanding what loads are. Right? Because it's a loads that would end up defining your analysis and also your design. Okay. So if you get your loads wrong, your designs are wrong. Okay. So that's how critical loads are to the overall behavior of structural analysis or design. Okay. So we have all these loads and then all of that, which you guys are aware of. Then one other thing that I need to look at before we 11:23. Okay. So now let's look at supports. You learned, I think, a few supports in year one. One of them is a pin support, okay, or a hinge support. Okay. And it's denoted by a triangular shape with a little bit of pattern design below it. And we learned that a pin support can resist loads in two directions. Okay. So we have, let's say, maybe Ry, then Rx. So Ry and Rx are resistance. Okay, so they are the reactions to loads. Okay. Newton's third law states that what actions and reactions are equal but opposite. So anytime we apply a load, we usually call loads actions. Okay, so some books will call all of these as actions. Okay. When you go through, I think Some of the design codes, like the European code, the EC2, the EC1. I think the EC1, yeah. So the EC1 is the one that has the loads and all of that in there. Normally they call the load actions. Okay. And then the resistance are called reactions. Okay. So a pin support is a hinge. So the hinge on the door in the lab right now, it can rotate, and that's how you can open the door, right? So because it can rotate, it means that it has no resistance to what rotation or to bending. Okay, and for that reason, the resistance to that rotation becomes zero, and that's how come MA, or the moment at that point, is zero, right? But then the door is not able to move up and down. Okay, and also you cannot pull it towards you or push it into the wall, which means that it is resisting any force you apply in these translational positions. So whether it's an upward or horizontal, or whether it's vertical or horizontal, these resistance will be applied. Okay. Then we have the ruler. Okay. So with the ruler, this is one way to represent it, or I think some books have it this way. So again, triangular in shape, but then have a bit of circular designs below it. All right. So these are your supports. With the ruler, you only have one reaction, RY. Okay. There is no RX, which means that rulers do not have resistance against horizontal motion. Okay. And we apply this a lot in bridge design. Okay. Normally for bridges, they're usually made up of steel structures, and steel structures tend to expand, or they respond to temperature changes. All right, significant responses, so thermal changes, which means that when the weather is very hot, the bridge will expand. When the weather is cold or cooler, the bridge materials will contract. Okay, so for example, let me just draw a simply supported structure over here. Let me draw another structure over here. We'll look at these ones later. Let me just draw this. We'll look at what this is. I don't worry about it. So since I've not taught this, sorry, let me just do this for us. Okay. So this is case one. This is case two. They are both bridges. What is going to happen with case one is that when there's increase in temperature, it means that your bridge is allowed to expand a little bit beyond the support. Okay, so this extra here come into play because there's temperature increase. All right. Now, when you come to this structure, because both ends are pinned, when there's temperature changes, this end on the right, or whichever end it is, cannot elongate. And once it doesn't elongate, it means that we have what you call stresses being built into the structure or into the bridge. So it's like pressure. There's pressure on it. I mean, let me go with layman's terms. So it's like there's pressure on the structure. Okay. And which means that this pressure would have to be released some way, somehow. All right. So this stresses that have been built up in the bridge would have to be released. And they can be released normally through the cracking of the bridge, or the or the bending of the bridge. So these are some of the things that are considered when doing all of these loads and supports and all of that. Okay. Then the other thing that we can look at, other supports, I just deal with only three, because they are the most common. There are the other ones. There's the link, there's a rock hide, all of that. Okay. Then we have what you call the fixed support. fixed supports. So with a fixed support, let me just redraw that on this side. Let me just bring it down here. So with a fixed support, it has three unknown reactions. So there's the Ry, there is the Rx, and there's also an unknown moment, M. So let me just call it M. Okay. So these are the three unknown support conditions. I mean, unknown reactions for the fixed. So for a pin support, there are two. Okay. For a roller, it's mostly one. And then for the fixed support, it's three reactions. Then we also have let me call this just some notes to take. Let me say types of structures. It's not really types per se, but it's more about how structures tend to respond to loads, or how they are able to provide stability when loads are applied to them, the way they provide their stability. So we try to group them based on that. Okay. So normally, our focus on this course will be what we call the moment resisting frames. Okay. And then we have the brace frames, the frames with shear walls. We have the pin jointed frames and all of that. They are just different types of frames, and it's just the mechanism by which they resist loads or transfer loads between the different structural members. Okay. So normally with the moment resisting frames, they are made up of beams and then columns. Okay. Normally, it's not always the case, but normally they're made up of beams and columns, or beams and slabs. Okay. Let me put it this way: beam, slabs, and columns. Okay. And with the beams, we call them the bending members. So another name for beams are bending members, because they resist loads through the bending action. Then we also have columns. We call them axial. Normally, they are called axial compression members. Okay. We'll explain some of these terms going forward. So when you get into, I think, third year, and you start doing your design, maybe in RCD and timber and steel design, you'd come across these terms a lot: bending members, and then axial compression, or maybe axial tension. But axial tension is normally not used for columns. They're normally used for braces. We have some structural members that we call them braces. Maybe when we get a chance, we can look at what some of these things are. Um, in basic structures, when trying to analyze a structure, you looked at equilibrium equations. Okay. These are typically equations of statics. Okay. And I think there were three of them, and we mentioned that summation of forces in the vertical direction equals 0, so that's one of them. Then summation of forces in the horizontal direction equals 0. Then summation of moments about a point is equal to 0. Right. So these were your three equilibrium equations. And then before you could even use this formulas, we should be able to define or tell whether a structure is statically determinate or not. Okay. Normally for beams and frames, we have three main ways or three types of structures based on their determinacy. Okay, in terms of their how statical, right? So statical has to do with the fact that they are stable. I mean, not they are stationary, right? Stationary structures. If a structure is statically determinate, what that simply means is that the three equilibrium equations are sufficient in solving or in analyzing that problem. Okay. So I think we looked at two, or you guys looked at three statically determinate structures. And that is when the unknown reactions is equal to the number of equations. Okay, so where R stands for unknown reactions. Then E stands for equations. And should I say, yeah, so then put the equation because it's not only the equilibrium equations per se. Okay. And then when the unknown reactions is more than the number of equations, then this becomes statically indeterminate. What this means is that these three equilibrium equations are not sufficient or are not enough to solve the problem. And I will need some additional equations. Okay. And these equations, we call them compatibility equations. We'll look at what they are. Then one other that we as engineers we tend to avoid is unstable structures, where typically there are more equations than the number of unknown reactions. All right. These are to describe what we call external statical behavior. Okay. You can sometimes have the number of reactions being equal to the number of equations, all right, but your structure can still be unstable. Okay. An example is this. So if I have three roller supports on this beam, okay. Now, with these three roller supports, these are my three unknown reactions. So this R1, R2, and R3. So here, the number of unknown reactions are 3. The number of equations are the same as the equilibrium equations. So E is also equal to 3. So since R is equal to E, then by definition, this structure is statically determinate. Okay. But internally, this is not stable. And the reason is that it has no reaction in a particular direction. Okay. Now, if I apply loads vertically, great. Your beam can resist these loads. But let's say I take away these vertical loads, then apply horizontal loads. Okay. None of the supports in this case has any resistance against horizontal motion, which means that assuming, let's say it's a plank, a board on some balls or bearings, it means that once I apply the horizontal load, H, the board will just slide off the balls. Okay. And once the ball slides off the balls, your structure has failed. Okay. So this method of trying to determine if a structure is determinate or otherwise is not foolproof. Sometimes you can have cases whereby inherently the structure cannot or inherently the structure would be unstable. We also looked at what you call the internal forces. Okay. And there are three of them: the shear force, the axial, and then the bending moment. So these are the internal behavior of the structure, right? In terms of how they're able to transfer loads from one end to the other, okay, or from one point to the other through these internal behavior. Okay. What we engineers are concerned with is being able to come up with diagrams. Okay. Come up with diagrams which would show us the general profile of these internal forces, right? So diagrams to show us shear force, axial force, and bending moments. Okay. And then from these diagrams, we'll try to look for the worst case scenario. Okay. And that's pretty much what design is. So we take the worst case scenario of the shear force, take the worst case scenario of the axial, and the same with the bending moment, and then we design against this worst case scenario. Okay. And in basic terms, that's design. So here the maximum is the absolute maximum, right? With structural analysis, you get to understand that if there's a negative in front of any value or a minus in front of any value, the minus only indicates the direction, not necessarily an effect on the value. Okay. So negative indicates direction, and then we look more at the magnitude of the value. Okay. So with your diagrams, when drawing these diagrams, you followed a sign convention, I believe. Okay. And then if it's axial forces you are looking at, if the forces are moving away from a point, that is, if they're in tension, it means that those forces are positive. Okay. And if they are moving towards a point of interest, in this case, then those forces are negative. Okay. Now for shear, if the forces are moving upward on the left of a point and then downward on the right of a point, they are positive. And then if they are moving down on the left of a point and moving up on the right of a point, they are negative. Then for bending moment, again, if the moment is clockwise on the left and then counterclockwise on the right, then it's positive. Then if it's counterclockwise on the left of the point and clockwise on the right of the point, then that is negative. So we call this one, with the bending, we call the positive a sagging moment. And we call the negative the Hawking moment. So some books will state some of these. Generally has to do with sign conventions. Okay. These sign conventions are not are not cast in stone per se. Some books would vary what their sign conventions are, but over the years, the most common, I think, with the Hebler and other textbooks, the most common is this are these sets of sign conventions. Okay. So here is tension for this guy here. This is compression. So tension is positive, compression is negative. Some books would flip it, will make compression positive and make tension negative. But I do believe that this is what you guys were taught. Can someone just answer that for me, just to make sure that this is what you guys did in your year one? Can anyone answer? I think the mic is off, so I don't know if. Sorry, come again.
All right. Yeah, they said yes.
Okay, all right, great.
Okay, they said they didn't do the axial forces. So.
Okay, that's fine. Yeah, mostly we don't. Mostly it's not touched because of the fact that beams are assumed that they are rigid when it comes to axial deformations. Okay. What we can do on the side, I don't know if I think the link to the lecture is also on the V campus. All right. So sometimes what you can do, um, even though you are watching from the screen using the laptop, you can also connect. Oops. You can also use the desktop in front of you, right? And then connect to Zoom. And then if you have a microphone or an earpiece or whatever, you can connect the earpiece um, to the computer, and you can also listen to whatever I'm saying. It ends up being the same thing. So in case I haven't asked a question, it's easy for you to answer right from there. Okay. You don't need to install Zoom. Okay. I think Zoom has an online whatever. So once you click on the link, I'm pretty sure you should be able to open the online without any installations whatsoever. Okay. That could also help. Maybe if I can get about 4 or 5 people doing that on a regular every week, so that in case of any feedback, I can get this from you guys. That will go a long way to at least make the class um, a bit what, a bit whatever, a bit conversational or interact. Okay, so the word is interactive. Now let's have an example. I don't want to say let's go for 5 minutes break and then we'll come back and then the lights are off. So I'll just straight away solve an example. When I'm done with the example, when it's more time, then we can take our break. Okay. So please pardon me. I know we should be taking a break from now, but let me just solve the example. A very straightforward one. So this is a simply supported beam. I'm pretty sure you know what beams are. We know types of loading. Some are simply supported. Some are cantilever beams. Some are overhang. Some are prop cantilever. All these you should have some information as to them. If for some reason you don't know what they are, you could, I don't know, you could let a TA let me know, or you can tell he could unmute and then you'd let me know. So as I'm teaching, if there's something you don't understand, you can at some point pause or stop me, then I can go over it. Okay. So let's look at a simply supported beam. So it has a UDL. Yeah, so it has a UDL, and then there's some concentrated or point load on this end. So the UDL, I think it's 12 kilonewtons per meter. The point load is 6 kilonewtons. And these are the dimensions. Okay. This is 4 meters, 4 meters. Here's 2 meters, sorry. My drawing it doesn't look drawn to scale. Okay, so 2 meters, 4 meters, 4 meters. So let me label the key points B, C, D, and E. All right. And the goal is to draw shear force and bending moment diagrams. Okay, so that's normally how these questions are set. Okay. So typically we have to look at what we call, so let me put here. So this is example 1. Let's say 1.1. Okay. Then solutions or solution. So with the solution, the first point would be to draw the free body diagram. Free body diagram. Okay. To indicate where all the forces would be. So I have here, I don't know which ones you guys used, but did you guys use the HAs or the AX or the RX? Which of these what was the name? Nomenclature was used for your analysis. So is it HA or E? So no, so this would be HE. Is it HE or EX or which again do we have? RXE. Which one are you guys going for? Is it the HE or the EX or the RXE? Sorry, come again. I don't know if my mic is low or something, but okay, I think it's me. Let me increase my volume a little bit. Okay, sorry, let's come again. Okay, so use the H. Okay, so then I'll just go with that approach. Okay, that's fine. So yeah, this is HE, and this is so VE. So HE, VE, VA, and then HA. So that's a free body diagram. Then you also have your loads right on it. I can just do the loads this way, it's fine. So this is your free body diagram. This is to show what all the forces are, right? So the loads are acting downwards, and we have your reaction components. So from here, you sum your whatever your loads using the equilibrium equations. Okay. So that's the plan. Let me see how far I can go today. Okay. So let's say summation of forces in the summation of forces in the horizontal directions are equal to 0. So there are two of them. There is a HA and there's a, oops, I made a mistake. Let me take this one out because it's a ruler, right? Not a pin support. It's a ruler, sorry. So there's no need to bring the HE. Let's clean that one up. So here, HA is equal to 0. Okay, because that's the only unknown that we have. Now, summation of forces in the y direction is equal to 0. There are 4 of these forces. So we have the VE, VA, the distributed load, and also the point load. So these are your 4 uh, forces in the y direction. Okay, so let me also highlight this one so at least they follow the same pattern. So here you can choose whatever your directions are in terms of which one is negative, which one is positive. So maybe in this case, upwards are positive, downwards are negative. These sign conventions are different from the internal behavior, please. Okay. The sign conventions here, the axial shear and bending moment are for the internal behavior. When you come to the external behavior, we are not too concerned which directions you choose your signs to be in. Any of them used to end up with the same answer. Okay. So here VA is upward, so I'm assuming that to be positive. So VA plus VE, they are both positive. Then minus the 6 kilonewtons because that one is acting downwards. Then minus, we need to convert the UDL into a point load. So we multiply the intensity, right? So the intensity is the height, right? So this is the intensity, which is the 12 kilonewtons per meter. This is the length, 4 meters. So we multiply the intensity by the length that the structure is loaded on. So it's pretty much trying to find an area of a rectangle. Okay. So this is akin to finding area of a rectangle. So that's the idea behind it. So it becomes 12 times 4, and all of this is equated to 0. Okay. So you can simplify it. VA plus VE, I think 12 4 is what? 48 plus 6, 54 kilonewtons. Great. But you see, the goal is to find these unknowns, right? To find the unknown reactions. I didn't mention that earlier, but the unknown reactions are, let me put that into this cage. Unknown reactions. So it's HA, VA, and then VE. HA 0, so now we found HA. But the second equation, which is the equation of summation of vertical forces, gives us VA plus VE. So 2 unknowns. And anytime you have an equation with 2 unknowns, it means that you cannot solve it with just one equation. So you need an additional equation to be able to solve that. Okay. So in this case, to do that with some moment about a point. Okay, so it could either be point A or point E. The idea is to eliminate one of the unknowns. Okay. So let's say with some moment about point E. Okay, so summation of moment about E equals 0. Moment is what? Force times perpendicular distance. Or should I say force moment? Because we have different types of moment. We have the area moment and then all of that. Mass moment. So the force moment is the force times the perpendicular distance. Okay. So if you are summing moment about E, then E becomes our point of interest. So with that, it means that our moment becomes VA. Okay, so the force times the distance. Okay, and this distance is where the load is applied to where we want to find the moment. And that distance, if you go back to the problem, is 4 plus 4 plus 2 plus 2, and that should give us 12. Okay. And the force VA will cause a clockwise rotation about E. Okay, will cause a clockwise rotation about E. So let me say clockwise. Then let's deal with the 6 kilonewtons first. We'll come back to the UDL. We have 6, the distance between where 6 is applied to where the load, where 6 is applied to where we want to find the moment, which is point E, is only 2 meters. Okay. And a 6 will cause an anti-clockwise rotation about E. So in this case, if I'm saying that clockwise is positive, then anti or counterclockwise is what, negative. So I can put a negative in front of the 6 and put a plus in front of the V, which is the same thing. Okay. Then for the UDL, that also causes a counterclockwise. So with a UDL, we need to first convert the UDL into a load. So the 12 times 4 converts the intensity of the distributed load into a point load, a point load in quotes. And this point load normally would act at the centroid of the UDL. Okay, so if UDLs are akin to being, or we assume they're like acting as though they are rectangles, and the centroid of a rectangle is at the center of the rectangle. Okay, which means that if I want to know the perpendicular distance, then it's simply half of this 4, all right, plus, so it's acting somewhere. Let me just draw it. It's acting somewhere in this space. So from between B and C all the way to E. That distance here, this dx is the distance for the UDL. Okay, so it's simply half of 4 plus 2 plus 2. So half of 4, let me do the socialist. Maybe we can use that as a reference. And all of this is equal to 0. Okay. So from here, you can do your computations, do your change of subject, do all of that. And then you'll see that your VA will be equal to 20, I think 5 kilonewtons. Okay. And if V is 25, we can go back into the vertical equation, substitute VA into that equation, and then find VE. Okay. Again, here VE will be equal to 29 kilonewtons. All right. So now we know HA, we know VA, we know VE. So we have all our external reactions. Okay. The next thing will be to calculate our shear force and then draw the shear force and bend moment diagrams. I'll just quickly draw that for us, and then we'll just see how it looks like. Maybe during the tutorial sessions, you can have the opportunity to do more of these calculations. Let's go back, draw our structure with the loads on them, and then these reactions now. Okay. So here's 25, this is 0, and this is 29, 6 kilonewtons, and then 12 kilonewtons per meter. Okay. So when you are dealing with shear force, there are so many ways by which we can draw shear force diagram. Okay. You can use, so you have the equation approach, okay, where you formulate equations for different spans of the structure. Or if you understand how shear force works, then you can focus on critical points or critical locations. Okay. So in this case, the critical point will be A, B, C, D, and E. So these are your critical points. So if you know how to go with that approach, great. Out of these two, the better approach is the equations method. And the reason is because the equations method would help you to understand how all these equations are derived. Because some of the topics you come across, you'll realize that you cannot just use the points method to uh, um, 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 solve the problem, right? In the sense that some of them, especially with like the area, so let me say with the deflection methods, some of the deflection methods, you need to formulate equations. You need to formulate some equations, and that's what you can use to solve some of these deflection problems. Okay. So let's so the shear force, let's say shear force at A. Again, shear force. Okay, sorry. So let me just write here shear force diagram because that's what we are doing next. Shear force diagram. I'm trying to draw the shear force diagram. Okay. So the shear force at A will be 25 kilonewtons. Okay. Anytime you are drawing shear force diagram, you would when you come across a shearing load or a point load, the shear at that point would or the you have to what's the word I'm looking for? You have to indicate the shear or the shearing behavior. You'll see what happens with the diagram very soon. Okay. Then the shear force, let's say between A and B will still be 25 because there's not really been any change in the shear. All right, 25 kilonewtons. Then the shear force between B and C, right? Because there's a UDL over there, I can formulate an equation for it. Okay. So I can say that that shear force is 25 minus 12 times X. Okay. Where X varies from, so here my X starts from here. Okay. Starts from B. So X varies from 0 to 4. Okay. So based on that, if X is 0, it's 25, and that'll be B, right? So so this is B and this is C. So shear force for at B, where my X is 0, will be equal to 25, right? 25 minus 12 over 0. Need to make sure that at every point I can see that you guys are connected in case the light goes out and I'm talking to myself. Just give me a second. Okay, so that's all right. So this will give us 25 kilonewtons. Then the shear force at C, when X is equal to 4, this becomes 25 minus 12 times 4. And 12 4 is what? 48. So this will give us minus 23 kilonewtons. Okay. So that next is to find shear force between C and D, which will be this shear force between C and D. That'll be the same as also then minus 23 kilonewtons. Okay. So this value is accurate up to D, just before the 6 kilonewton punch load. So let me state that. Okay. So so this is just before, which means that um just after D, it means that we have to include the punch load. So it means that, so this is at D. Okay, so this is this one is this is at D before, so D before, okay, and then D after. Let me just write that one first before I circle anything. Becomes minus 23 minus 23 minus 6, and that'll give us minus 29 kilonewtons. Okay, now I can circle, so this is D after. Okay, then again, shear force at E. Oops, different color. Shear force, let's say between D and E. So again, let's say at E. If there are any questions, you can always stop me and then ask. Or as I said, you can just go to Zoom. You can just go to the V campus on the main computer in front of you. Then just join, and then you can use your earpiece if you have them, some of them around you. And then you can join the class as well. And then you can ask your questions. Okay. What again? Number 24. Okay. So at E, we have to just before and just after. These are some of the things we normally do with shear force before and after. It's a bit interesting. So just before, um, so just before the shear force at E, sorry. So just before E will be equal to the same minus 29 kilonewtons. Then again at E, but this will be just after E. Just after E, that will be minus 29 plus 29. Okay, this should give us I'll explain some of them. I think I'm jumping a few steps with the idea that we have already done this in our first year, so I don't need to spend too much time over here. Okay. So just to explain a few things, these are the critical points. The critical points are A, B, C, D, and E. So if you can find your shear at A, find your shear at B, find your shear at C, and then at D, and then E, we should be able to draw our shear force diagram. Okay. But one thing to take note is that when you come across a punch load, there'll be a shearing behavior at that punch load. Okay. So with this particular problem, there are 3 points that has punch loads. One is point A, point D, and then point E. They have the punch loads. Okay. And what that means is your shear force diagram will look like this. A, maybe B, C. Let me just move this a little bit. B, C, D, and E. So A, B, C, and D. So at A, your share is 25. So that's a vertical. And then between A and B, the share remains constant. There's no change in your share. Okay. So again, at B, your share is 25 kilonewtons right here. Then at C, it goes to negative, oops. At C, it goes to negative 25. Okay. So it is 25 at B, and at C, it goes to negative 23, which means that you have to draw a line to join these 2 points. Okay. A straight line. Well, mine doesn't look straight, but okay. And the reason why we have that, it has to do with the fact that we're looking at equations, right? When I think you were looking at gradient and all of that linear equation, you were like y is equal to mx plus c, right? Y is equal to mx plus c. If c is equal to 0, then y is equal to mx. Okay. And this is a linear equation, okay, which means that you end up with lines drawn in this form. Okay. So this is a linear equation. So anytime you have an equation whereby the exponent of the x or the variable, the independent variable is exponent 1, then that becomes a linear equation. So let me just write them nicely over here. So let's say y is equal to, let me say mx k, so mx exponent k. If k is equal to 0, then y, let me put plus c over here, so that if k is equal to 0, then y is equal to c, and that is a constant, okay, or a constant line. I think I'm running out of space. Let me see. Let me put this right down so that it follows. I'll just create a box for it because it's just extra information. So if y is equal to mx exponent k plus c, where k, if k is 0, then it means that y is equal to c. Is this c? No, sorry. M plus c. Then and that way I can just then make it simple by taking away the c. So y is equal to m. And if y is equal to m, then this is a constant. Okay. So normally your line will be a straight line. Okay. Now when k is equal to 1, then y is equal to mx. Okay. And this will give us a linear variation. Okay. So your line can either be this shape or that shape, depending on whether there's a negative or not in front of the equation. Now, when k is equal to 2, then y is equal to what? Mx squared. And now you are going to the territory of what? Parabolic behavior. Okay. Now your curve would either be this way or that way. Okay. Then the last one we can look at is when k is equal to 3, y is equal to mx cubed. So as the name implies, this is what? Cubic. So parabolic is the same as quadratic. Okay, let me just put that over here. Quadratic. Then this is cubic. Cubic is pretty much the same. It's similar in terms of the curve to the parabolic, but this one, the curve is a bit sharp. It has a higher gradient than that of the parabolic. All right. So these are some of the information that if you know or if you have them, helps you to be able to draw these diagrams easily. Okay. Yeah, so back to our diagram. So between B and C is linear because there's a linear equation over here. This is our linear equation right here. Let me see if I could change the color. Okay. So this is our linear equation right here. 25 minus 12x, and the highest exponent of x in this case is exponent is 1, which is a linear variation. So then between C and D, it remains constant. But at D, because it's encountering a point load at D, we'll have that shearing behavior. Okay. So here is one shearing behavior, now another shearing behavior. Okay. Then between D and E, it is constant. And then when it gets to E, another shearing behavior. Okay. And this here. Okay. And this becomes your shear force diagram. Okay. Well, this is your shear force diagram. The portion above the horizontal axis is a positive, and the portion below is a negative. Okay. So normally it's advisable to write key values on it. Here's 25. This is 23. And this is 29. All right. So per this diagram, your maximum shear force is 29 kilonewtons. Yes, 29 is negative, but again, negative only indicates direction. All right. So your maximum shear force is 29 kilonewtons. Maybe absolute, so that it makes sense. Algebraically, it will make sense that okay, SF max should be absolute. Now, if you look at the short diagram, you'd realize that at some point between B and C, the linear line crosses the zero axis. All right. So means that at some point here, your shear force is 0. So here at this point, shear force is 0. We don't know what that point is. And usually it's good to know the location at which your shear is 0. And the reason has to do with the fact that usually between a span or between somewhere between the beam or on the length of a beam, if your shear force is 0, that's where your maximum bending moment would be. All right. So now let's look at the bending moment diagram. Again, it follows similar premise. So with our bending moment, the interesting thing about bending moments is that it's best drawn using equations. All right. But again, you can also look at critical points and then use that to draw a bending moment diagram. If only you understand how this whole thing works. Right? This whole exponents and all of that, and what the shapes would be if you had to draw them and all of that. Yeah. So I'm just trying to bring back. Okay. So with a bending moment diagram, you look at spans. Okay. The best is to look at spans. So there are 4 spans. So the spans that we have here are spans AB, spans how should I even do this to make it easier for me? Okay, so section AB is fine. Spans BC, span CD, and then span DE. So these are the 4 spans that we are looking at. Okay. So let's start with span AB. This is moving a lot. So span AB. All right. So with that one, we can assume that we are somewhere here. We are somewhere in this space. We are somewhere here. All right. So span AB, it means that we can cut a section between A and B. Okay. So let me just. So if I cut a section between A and B, this is what I have. Okay, so I have my reaction here. So here I have my, and anytime you cut a section on a beam, right? Before I forget that, when you cut a section on a beam, so let's say if you have a beam like this, now you cut it into 2, maybe along any arbitrary section. By the definition of internal forces, it means that you would end up with some reactions which are equal and opposites. Which are equal and opposite. So that once you add this together, everything goes to 0. Okay. So the same applies over here. Once I cut this section between A and B, I'll introduce these support reactions. Okay. But with bending, what's of interest to us right now? It has to do with the bending moment. Okay. So I can take that one away. Okay, sorry. I can take, so let me just write it properly. I can take that one away. And then, so let me call this maybe KK. So find the bending moment. Let me take this guy off. Bending moments. Okay. So if this distance here is, if the distance here is X, right? So X is between A and B, can be any value, right? X could be at A, X could be at B, or anything between A and B. And this is 25 kilonewtons. Okay. So let's say summation of moment at K is equal to 0. So this is K, this point is K, okay, this point is A. Okay. And that's the reason why I didn't bring the reaction here, because I'm taking moments about K. And once I take moments about K, VK component will be 0 in terms of the moment. Okay, so take a note. VK is not 0, but moment due to VK is 0. And there's a reason I didn't bring it in my diagram here for simplicity's sake. Okay. So here it means that VA times X minus B moment at K equals 0. So this equation, which means that VA X, or let me write it this way. Bending moment at K in this case is equal to VA times X. Okay. What this means is that X, let me put into brackets, X can vary from 0 to what? 4. Okay. Where 0 is at A and then 4 is at B. Okay. So where X is equal to 0, it means that our bending moment will be the bending moment at A. That's where X is 0. So that will give us what? 25. Let me make this one. This is 25X. So it becomes 25 times 0, and that will be 0. When X is equal to 4, that's at B. Bending moment at B becomes 25 times 4, and that will give us 100 kilonewton meter. Please take note of the unit of moment. It's force times distance. Okay. Then what again do we have? Okay. Now let's go to span. The next span BC. So span BC. Again, we shift our goalposts. Okay. Shift our goalpost. So now instead of cutting a section at K or between A and B, we come and cut a section between B and C. Let's call that section maybe NN and N, right? So we cut a section at B and C or between B and C, which means that our beam will now look like this. So this is a UDL. So this is A, this is B, and this point is N. Somewhere between B and C is N. In solving this problem, there are a number of scenarios we can use. Okay. The distance from here, so this is 4. Yes, or between B and N is unknown. Okay. So we can decide that, okay, let's make the entire length here X, so that between B and N is simply X minus 4. So that's one way to look at it. So, we can look at we'll look at the other option soon. Okay. So the load here is 25 kilonewtons for the reaction at A. So here's 12 kilonewtons per meter. Again, we need to find this moment here, BMN. Okay. So again, we come summation of moment at N equals 0. So it becomes VA times X, right? Between A and N is X, minus, then we have the UDL also come into play. So for the U, that becomes minus 12 times its loaded length, which is X minus 4. And then times X minus 4 over 2. And then, so this should be pretty much, this should be equal to BMK, all right? I'm not going to go through, let me just shift this a little bit to the right, so that all of this is equal to BMN, not BMK. Okay. So at, in this case, our limits for X will lie between B and then C, because that's at this point we are dealing with B and C. So at B, X is 4, and at C, X is what? So if this is, I didn't write those earlier, let me just put them here again. This is 4, 4, 2, 2. So at B is 4, and at C is 8 meters. Okay. So bending moment at B, where X is equal to 4, will give us so 25 times 4 minus 12. So this will give us 0, right? 4 minus 4 is 0. This is 0 over 2. So that should give us 100 kilonewton meter. Okay. So these two should be the same, which makes sense. All right. Okay. And the bending moment at C, where X is equal to 8, will be equal to 25 times 8 minus 12 into bracket 8 minus 4 times 8 minus 4 over 2. My pen is not writing. The screen is tired. Okay, let me see. Hopefully you are back. Oops. Okay, great. It's back. So this should give us, I think, if I'm correct, 104 kilonewton meter. So this is one way to solve it. Okay. So let me call this one case 1. So this is case 1. For case 2, let me just try to be a bit lazy. So for case 2, I'm just trying to redraw everything over here. So for case 2, what is happening is that instead of all of these, I can just do it this way. So again, I measure here. I know this is 4. I can just make this nx. All right. But if I make this nx, then it means that the limit of x will change slightly from 0 at B to 4 at C. So this is B and this is C. So then these are my limits. And that will change my equation slightly for bending moment at N. So here the bending moment at N will be equal to VA 4 plus X. Okay. Minus 12 times X over 2. Okay, so this becomes your equation and it will end up with the same answer. Okay. So bending moment at B, where X is 0, will give me VA will be equal to VA. VA is 25. So 25 times what? 4, because X is 0. And this whole thing will be 0 because X is 0. And we'll still get what? 100 kilonewton meter. And then the bending moment at C, where X is equal to 4, will be 25. 4 plus 4 minus 12 times 4 over 2. And you'll see that you get the same 104 kilonewton meter. Okay. So regardless whether it's this option or that option, you can decide on which one works for you, and then you go with it. So it's one or the other. You don't do both. Okay. So that's section B, section A, B, and section B, C. Now let's look at the other section, which is span CD. So we span CD, then we are looking at somewhere between C and D. All right. So between C and D, let's cut a section again. All right. So this is P, P, P. And please take note, when you cut a section or when you cut a beam into 2 sections or 2 parts, you can choose either of them. You can either choose the left side or choose the right side. Okay. Normally, it's easier to choose the left side because of how diagram progression is. But sometimes, or once in a while, you come across structural analysis problems, which will require you to choose the right-hand side. Okay. So a good understanding of the sign conventions will come into play. I'm sure one of these days we'll come across such questions and then we'll see how we can work our way around it. So let's look at span CD. So span CD, again, from the left-hand side. So I have my beam, my reactions, my UDL. Okay. So this is what A, B, C, and P. You don't know what P is. Okay. So let's look at it. I'll go with I'll go with just case 1 for this case. I won't do the 2 of them. All right. I wanted to explain to you guys the thinking behind some of the things that we do. So here's 4. This is also 4 meters. And this whole thing is x. Then here's what's x minus 8. Okay. And then we have all the reactions. This is 12 kilonewtons per meter. This is 25 kilonewtons. We have all of that over here. So we want to find this moment, BMP, bending moment at P. Okay. So the bending moment at P will be equal to VA X minus 12 times 4 times 4 over 2 plus x minus 8. Okay. Again, if you don't understand anything, let me know. I'm assuming that we all understand it, so we are good to go. Okay, I'll come back to something quickly. When I start drawing the diagram. So the bending moment at C, because our key point is C between C and D. All right. So between C and D, the x will be at C, x will be 8, and at D, x will be 10. The 10? Yeah, 10. Okay. So at C and D. Okay. So bending moment at C will be equal to when see here, when x is equal to 8, that is C, will be equal to 25 times 8 minus 12 times 4, 4 over 2 plus 8 minus 8. So that'll give us 0. And then when you compute it, you should get 104 kilonewton meter. Then the bending moment at D, when x is equal to 10, will be 25 times 10 minus 12 times 4, 4 over 2 plus 10 minus 8. I'm just substituting the value of x into these equations. Okay. And that'll give us 58 kilonewton meter. So once we have that, then our last span will be span DE. Okay. So now let's look at span DE. So span DE, let me just draw again from the left side. So we have all of that. Okay. So this is the 12 kilonewton per meter. This is my 25 kilonewtons. This is my 6 kilonewton. Okay. So this is A, B, C, D. Let me call this one Q. Okay. So back to the structure here. I'm cutting a section somewhere here. Okay. So this is Q, Q. So I can either use this one to be easier to use the right-hand side than the left-hand side, but we're just, because we are just progressing from the left, so I'll just go with that approach. Okay. So here I need to find the moment here, B, M, Q. Okay. So let me put in my yes, 4, 4, 2. And this whole thing is x, and this is x minus 10, right? Yeah, x minus 10. So our bending moments, BMQ, will be equal to the 25, which is the what's the name? The reaction at A. So 25 times x minus 12 times 4. It would be a pretty long equation. Let me see. Let me see if I can move it a little bit. Okay. So times 4. Then bracket opened, 4 over 2 plus 2 plus x minus 10, then minus 6 into bracket x minus 10. Yeah, it's quite long, but that's how it's supposed to look like. Okay. So our limits would be, x will be from 10 to 12. So that's from D to what? E. Okay. So the bending moment at D will be equal to 25 times 10 minus 12 times 4 times 4 over 2 plus 2 plus 10 minus 10 minus 6, 10 minus 10. So you see that this one goes to 0 because 10 minus 10, so it's fine. And then when you do the computations, you see that you end up with an answer equal to 58 kilonewton meter. The bending moment at E, which is the last one, will be 25 times 12 minus 12 times 4, then bracket open, 4 over 2 plus 2 plus 12 minus 10, then minus 6, 12 minus 10. And this should give us 0. And these are the values for the moment. Yeah, great. It's quite interesting with moment calculations, all right? It's taking long because I'm exaggerating, trying to explain everything to you guys. But usually when you're solving these ones, it's a bit more straightforward. So let's see, let's draw the moment diagram. This is A, B, C, D, and E. Okay. Now let's take note of something. The bending moment at A, bending moment at A is 0. Where is it? Bending moment at A is 0, right? Bending moment at B is 100. At C is 104. At D is 58. Then at E is also 0. Okay. So bending moment at A is 0. At B, it's 100. At C is 104. So this is 0, 100, 104. At D is 58. And then at E, it's 0. So how do we draw this? What shape should this be in? That is one of the challenging questions that students tend to face. How should overall, at least getting the points can be done, but what should be the general shape of the point? Okay. Now, one of the rules of thumb is to look at what loads are between the spans. Okay. Now, if we take between span A and B, there's no load between A and B. Okay. So because there's no load between A and B, and looking at the equation, you'll see that the equation here, this equation VA minus X is a linear equation. Okay. So going back to this right here, so Y is equal to MX is a linear equation, which means that between the points A and B, you will have a straight line. Okay. So between A and B, I will have a straight line. Okay. Now going back, so now our focus is now between B and C. Between B and C is where we have the UDL. Okay. So once we have UDL, we come back to that, which is the span BC. Okay. So span BC, here is our equation. Okay. So it's VAX minus 12 into bracket X minus 4, X minus 4 over 2. If you were to expand this part of the, or to expand and simplify this part of the equation, you would realize that the maximum, the highest exponent of X will be squared. Okay. And by so doing, this makes this problem a quadratic or a parabolic problem. Okay. Whether I go with option, whether I go with case one and case two, is the same thing. It's even easier to even show in case two. So case two, you would see that it becomes what? So what 4VA plus VAX, oops, x should be bigger, minus 12x squared over 2. All right. So right here, you can easily see the square component, even from this calculation. If you are to expand, either way, they will have the highest exponent being 2. Okay. So that means that our equation is a quadratic equation. Now, the challenge with this quadratic equation, all right, so let me just, so this is what, 100? Maybe somewhere here is 104. Is it going to be like this? Is it going to be, maybe let me see, let me just, is it going to be something like that? I mean, it's still a curve, but it's not, if I bring this one down a little bit, maybe it could help me. Okay, maybe, so is it going to be this curve? Okay, where between points B and C, there's no highest point? Or is it going to be this curve? Let me just redraw this whole thing here. Okay, where maybe it goes up, then it comes down. Okay, these are two different curves. With the second curve, you have your highest point. Okay, it being between or occurring between B and C, but with the case two, with the case one, sorry, with the case one, your highest points would end up being at the 104. All right. So how do you know which of these curves work for you? Okay. And usually, that is where the what's the name? So that is where, what's the name? That is where your shear force diagram becomes important to you. Okay. So if you go back to the shear force diagram, where's my shear force diagram? Okay, you see. If you go back to the shear force diagram, right on the side, between B and C, there's a point where the shear force is 0. Right. So because there's a point where the shear force is 0, it means that if you have to draw your bending moment diagram, there will be a point on that moment diagram between B and C where the moment will be maximum. And this is explained through differentiation. Okay. If you differentiate the moment with respect to distance, you get, oops. If you differentiate moment with respect to distance, you get the shear. Okay. So where differentiating moment with respect to distance x gives you 0, so that's where the shear is 0. This would only occur where you have your maximum or minimum moment. So this means that case 2 would be the better option to go with. Okay. As to what your maximum value would be, you need to find the distance x, which would be the distance where the distance here between B and where the shear force is 0. Okay. And once you find that distance, you can easily determine the moment. So somewhere between B and C, if you can find that distance where the shear force is 0, if you plot that value of x into the equation, the moment equation, you would end up with the value for the maximum moment. Okay. So in this case, I can go ahead and draw my plot to look like this. Okay. So somewhere here, there's a maximum moment, which we don't know yet, or we can easily find. Okay. Now, when we come to span CD, so span CD, this is our equation. All right. And then the highest exponent of x is 1. Okay. So this gives us a linear equation. So once the equation is linear, it means that between C and D, we should have a straight line. Okay. So please, if it doesn't look like a straight line, this is a straight line, and then this is a curve. Let's take note. So here's a curve. This is a line. This is also a line. Okay. Then again, between D and E, the highest exponent of x is 1. So again, this makes this equation again linear. And then you can join the 2 points now. So in effect, this becomes your bending moment diagram. Okay. The goal is to find the maximum points. Okay. And to find the maximum point, which is somewhere between B and C, we can easily, so let's say to locate, let me just write over here, to locate maximum moment. Okay, so this occurs between B and C. So the steps are out, right? Here equation for span BC. Okay, that's one. Then equate it to 0 and find x. So let's see what this is. Let's go up to where? Okay, right here. Right to this space. So these are too many colors. Why not deleting? Okay, oops, I think I've done what I'm supposed to delete. Okay, so this is our equation here, 25 minus 12x. Okay, so we come back all the way down, 25 minus 12x, and we equate this to 0, and we find the x. So x is simply 25 over 12, and that'll give us what? 25 divided by 12. That'll give us, I think 2.0833. 0.83 is fine, meters. Okay. So bending moment max. Okay, it occurs between B and C, right? The bending moment occurs between B and C. So I come to between B and C. Where are you? And then maybe I go with this option because I think that's the easiest to go with. So let me go with this option. Okay, great. So in that case, bending moment max is equal to, so here, this x is equal to 2.083. It becomes 25 times 20 and sorry, 4 plus 2.083 minus 12, 2.083 times 2.083 over 2. And this will give us what? Anyone with a calculator can check the value for me, please. So this should give us 126.05, I believe. Am I correct? So what it means that at some distance, here, oops, a different color. Okay, some distance here, 2.083 meters from E, we have let me delete this guy here. So the maximum is somewhere here. It's not right. It's a little bit just beyond the center of B and C. Please take note. It's not at the center. So this becomes 126.05. Okay. So that's the maximum moment on this structure. So again, take a note, please. This area is a curve, and then the rest are lines. Okay. So I think that should bring us to the end of today's class, I believe. I'll cover what I wanted to cover for today. I was hoping we could start deflections, but that's fine. Any questions for me? Any questions for me? So let's try and then go with this second approach where you come to class, then some of you should log into the computers around, at least since you're all behind computer. If one person from each three-member group logs onto the computer, at least, I mean, you can share mics, just the mic if there are any questions you want to ask, and then it'll be easier that way, right? So that it doesn't become like me talking throughout and you guys listening throughout, and don't get anything. I don't see what you're getting, and you're all over the place, and I'm not happy. Yeah. Please ask your question. Sorry, I can't hear you for whatever reason. The voice is not too. Am I what? Sorry. There's a lot of feedback, unfortunately.
I think she's saying she needs to get the answer for the maximum bending moment. She didn't get the answer.
So how come your voice is clear and hers is not clear?
She's using the mic.
She's doing what?
She's using the mic. 141.70166.
Wait, you got a different answer to mine? Oh, sorry. And I can't really hear you at all. I think the mic has a problem.
Hey.
Yeah, hello. Yeah.
Yes, please. I was saying that I didn't get the same answer, but now I've gotten it.
Oh, okay, all right. We are good, right?
Thank you.
You're welcome. Yeah. So if the mic will be a challenge, I mean, almost everybody has earphones because we all use smartphones, right? Maybe those who have the Bluetooth earphones might not work because I don't think that PCs on campus have Bluetooth though, but you can buy yourself a simple earpiece. I mean, it doesn't cost that much. So if you want to talk, maybe you can approach the PC so that it becomes, I can hear you a bit clearly. Otherwise, I think the mic is struggling to bring out your voice. Yeah.
Yeah, please, I've now asked, like, where did you get the 25 minus 12?
This one.
Yes.
This one right here. I got it from the shear equation. So write shear equation for span BC. So if I go back to the shear equation, which is here in this zone, right? So between B and C, my shear equation is 25, as you can see, is 25 minus 12x. So that's the shear equation between B and C. And that is where the maximum bending moment would occur, right? So if you go back to the diagram, between B and C, you have a point where there's 0, all right?
Yes.
Yeah. So we are equating it to 0 and then find x and use x to find the maximum moment.
Thank you, sir.
You're welcome. Hopefully in the near future, they can fix microphones at certain places in the room so that when anyone talks in the classroom, you can hear the person. So you don't need to have one particular mic. You can have about 4 or 5 different mics positioned at different locations in the room.